First of all, I would like to explain about the introductions. Application of derivative and integration calculus in Malaysia Geoscience are mainly found in geophysical data processing, hydrological modeling, and petroleum engineering. These mathematical tools are fundamental to modeling continuous change and optimizing solutions for complex and subsurface problems. Derivatives are frequently employed to analyze the rate of change in various geoscience phenomena. These include rainfall intensity, river flow, soil erosion, soil deposit, and slope stability. A key application of this analysis is understanding the occurrence of floods and landslide in vulnerable regions such as in Selangor and Pahang. Furthermore, derivative calculation can determine the rate of change in rainfall intensity over time. This is a calculation about derivative. In geoscience, the topic of integration usually refers to combining different types of data and methods. For example, remote sensing, geophysical surveys, GIS, and well log to form a comprehensive understanding of subsurface and geological process. The Malaysian case study highlights the integrated approach in several key areas. Integration can be used in geodisaster assessment and urban planning. This assessment can study landslide and flood risk mapping. This study can be done in urban areas which is in Sabah and Kedah. Geoscience data is spatially integrated using Geographic Information System (GIS) to assess land condition and vulnerability to hazards such as landslide and floods. This allows the demarcation of suitable zones for urban development, with findings showing that 8% of cities have moderate to high land constraint.
This case study showed that urban and coastal lowland area in Selangor experience measurable land subsidence due to the factors such as groundwater extraction and soil consolidation. Remote sensing studies showed that the order of approximately 8 millimeters per year of subsidence in some area in Selangor shows that a decreasing rate over time from 10 millimeters per year to 6 millimeters per year shows that the subsidence may decelerate with time if external forcing is reduced. So, if a constant or increasing rate over long periods in real observation data will signal subsidence hazards. Urban planners and engineers can use the instantaneous rate DT to estimate the future land levels and project infrastructure settlement or design mitigation such as controlled pumping schedules. That's all. While my own solution is exactly the same as ChatGPT, and which is d over dt in brackets 10t minus 0.4t, and the 0.4t, the t can be replaced by 0, 5 and 10. So we need to divide by 3 parts, such as part 1 is the baseline, which is 0, part 2 is 5 years, part 3 is 10 years, and for the 01 is we got 10 millimeters per year, the 5 is 8 millimeters per year, and 10 is 6 millimeters per year, which is exactly the same as the answer ChatGPT showed. For my conclusion, this case study demonstrates how derivatives can be applied in geoscience to know the connection between subsidence rate in coastal Selangor, Malaysia. By using derivatives, urban planners and engineers can know the future land height and to improve their solution for each height that will occur. Therefore, derivatives are very important in avoiding every possible risk that can caused by subsidence in Malaysia. That's all. Thank you.
3662. Today I will explain how derivatives are applied in geoscience using a real-world case study from Cameron Highland, Pahang. Cameron Highland is a mountainous area in Malaysia that frequently experiences landslides. This is mainly due to steep slopes and heavy rainfall. During intense rain, large amounts of water flows over the ground surface, which can weaken slopes and trigger landslides. In this case study, surface runoff, denoted by Q, is In this case study, surface runoff, denoted by Q, is modeled as a function of rainfall intensity R. The mathematical model used in Q equals 0.002 R squared. This equation shows that runoff increases as rainfall intensity increases, but not at a constant rate. To understand runoff increases during heavy rainfall, we use derivative. By differentiating Q with respect to R, we obtain dQ over dR equals 0.004 R. This derivatives represents the rate of change of runoff help us understand and quantify how change in rainfall can affect slope stability in areas like Cameron Highland. In conclusion, derivatives are a useful mathematical tools in geoscience because they help us analyze how quickly environmental conditions can change and support better landslide risk assessment.
Alteration in the Padas River Basin Sabah. Flooding is one of the most serious geoscience problems in Malaysia, especially in Sabah. This is because Sabah has steep landform and experiences heavy tropical. This factor causes rivers such as the Padas River to respond very quickly during storm events. In this study, we focus on how river discharge change over time. Discharge is represented by the Q. The initial discharge is written as Q of 0, which means the question geoscience is how quantitative methods can inform geoscience interpretation and management. Hydrology observation during a storm event in the Padas River Basin provide the following data.
First, the formula used is dq over dt equals minus q over k. Next, substitute the given value into the formula. dq over dt equals 350 minutes q over k. Then, rearranging the equation, 400 k minutes 500 equals 150. Divide both sides by 400. K equals 150 over. Simplify the fraction. K equals 3 over 8. Next, take the natural logarithm on both sides. Natural log 3 over k equals natural log 3t. Finally, the value of k is obtained. K equals 3.05 hours. Hence, the required value of k has been determined. Lastly, in conclusion, the attenuation of fluid events in the Padas River Basin represents the rapid hydrological response that occurs in the basin when high rainfall is involved. As the discharge rates peak intensely in only 3 short hours when fluid events are intense. Indeed, the rapid hydrological response rate affirms that the region is more prone to flash flood events that might pose a threat to general public and the concerned infrastructure as well. However, the application of mathematical model will help represent the importance of fluid management and the protection of the general public living in flood-prone areas such as Sabah. Thank you. Thank you. Thank you.
My name is Aizani Nasban bin Abdurrahman. My nometric was E253660. So my case study was application in integration of geoscience, and my case study was estimating sediment accumulation volume in Sungai Kedah. First of all, I will present about my background. Sungai Kedah is a vital river system for the Rice Bowl state of Kedah, Malaysia. It plays an important role in supporting irrigation for paddy cultivation and managing urban drainage for the city of Alor. However, during intense monsoon seasons, soil erosion from upstream agricultural areas transport large amounts of sediment downstream. This sediment gradually accumulate along the riverbed, reducing the river's hydraulic capacity and increasing the risk of flash floods. Therefore, estimating the volume of sediment accumulation along Sungai Kedah is essential for effective flood mitigation and sustainable river management. The geoscience question for the study was, how much sediment volume is deposited along a 10-kilometer stretch of Sungai Kedah during one monsoon season? In conclusion, this case study demonstrates how mathematical techniques such as geoscience to model real-world environmental problems. By accurately representing sediment variation along a river, meaningful prediction can be made to support sustainable river management and reduce flood risk. That's all from me.
In conclusion, this study has successfully demonstrated the basic concept of calculus, which are derivative and integration, which have played an important role in the field of geoscience, especially studying and predicting disaster in Malaysia. In derivative application, the rate of change of phenomena such as rainfall, surface runoff, soil deposition, and land management can be analyzed more precisely. This can help geoscience detect disaster risk and take early reactions. Next, derivative allow the calculation of accumulated quantities such as the amount of rain, volume of sediment, and change in ground level in a certain period of time. However, this study has shown that the exact outcome of a decision does not depend entirely on mathematical calculation. A very simple model can be used by an inaccurate and obvious interpretation that will cause a negative impact on the actual planning. Therefore, understanding the geological process is very important to produce an accurate analysis that can be used in Malaysia through mathematical integration, calculus, and real data. Finally, this project has shown the effectiveness and importance of the subject of basic mathematics in the application of geoscience and is able to increase students' understanding of the role of mathematics in solving disaster phenomena and environmental problems in Malaysia.